have our usual Q&A. Eleni, the floor is yours.
Thank you very much for the invitation. Before starting, I just wanted to mention that it's a bit sad for me to give this talk just a week after the death of my friend and collaborator, Cen Zhang, who was also an organizer of this series. So Cen is someone we're going to miss a lot. Actually, most of the stuff I'm going to talk about, we did together. So this talk is basically dedicated to his memory. Okay, so I will basically start with an introduction to SMEFT, and SMEFT in particular as a way to look for new physics at colliders. So I know that of course this is the All Things EFT series, and we already had quite a few nice talks on SMEFT, but I thought a bit of repetition never hurts. Then I will move on to discuss a bit how SMEFT enters in a lot of different observables that get measured at the LHC, and how theory has progressed over the recent years to give us precise calculations in the SMEFT, and try to motivate a bit these precision calculations and how they are useful to learn more about UV physics. And then for the second part of my talk, I will discuss global fits, first in the top sector, and then also combining the top and the Higgs sectors, which are very deeply connected within SMEFT. So at the LHC, basically, we have been lucky to discover the Higgs, and what we've seen so far is that the couplings of the Higgs seem to be in good agreement with the standard model predictions. You see this summary plot here by Atlas, where the coupling of the Higgs to the fermions and the gauge bosons seem to be in agreement with the standard model predictions. On top of all the Higgs measurements, of course, there is a lot of work going on in measuring a lot of other observables at the LHC. Again, this is another summary table from Atlas, which shows that a lot of different processes, some of them, in fact, very rare, are getting measured at the LHC and compared to the predictions of the standard model. So far, everything seems to be in good agreement with the standard model predictions, but of course, this doesn't stop us. In fact, it motivates us to look harder for deviations from the standard model predictions and signs of new physics. So there are basically two directions in which we hope to find new physics. One is a bit model dependent, so we pick our favorite UV complete model, and then we search for the new particles which exist in these models, which typically appear as resonance peaks in various distributions. So that's one way of looking for new physics, and the LHC is doing a lot of searches in this direction. So far, basically just setting bounds on various masses of new particles. The second way of looking for new physics is by a more model-independent way, and this involves effective field theory. So in effective field theory, basically we try to measure precisely the interactions of the standard model particles and compare these interactions to what the standard model predicts. So these new interactions that are described by effective field theory typically lead to deviations in the tails of distributions, like the ones shown here in this plot. So just taking a simple example, how how does effective field theory come up? We can take again a very simple example where we have a heavy copy of the Z boson. So we call this the Z prime. This Z prime couples to a quark-antiquark pair, which means that it will mediate quark-antiquark scattering. Then this amplitude here will depend, of course, on this propagator, which will have the mass of the Z prime in the denominator. So provided that the energy which goes into this collision is smaller than the mass of this Z prime, what we can do is basically Taylor expand this propagator, and then we end up with some power series, which are basically an expansion in 1 over the mass of the Z prime. And effectively, what we've done here is to integrate out this new heavy particle, and we end up with a 4 fermion contact interaction, and the strength of this interaction is suppressed by the mass of the particle that we have integrated out. So starting with the UV Lagrangian, where we have this Z prime, what we end up with is the standard model Lagrangian, which we had before. And on top of that, we have a series of dimension 6 operators, which are suppressed by the mass of the Z prime. So schematically, how does that help us to find new physics using effective field theory? So you can see in this simple picture here. In collider experiments, our energy, which is available for the collision, is limited by the energy of the colliding particles. So if we have enough energy to produce a particle, we will see it here in this distribution, for example, as a peak. So this is how we will see, for example, the Z boson in some dilepton invariant mass distribution. Of course, if there is another particle which is much heavier, and therefore we don't have enough energy to produce it directly, so we will not be able to see this peak, what we can see instead is these small deviations in the tails of this distribution. And by precisely measuring these deviations, we get an indication that there is basically some new heavy particle beyond the direct collider energy reach. And this gives us a way to probe new physics going to scales beyond what we can directly probe. So the advantage of effective field theory is that is typically considered to be model independent. This means that it works for any type of heavy new particle, and the final effect of these new heavy particles is basically these higher dimension operators, which get added to the standard model Lagrangian. So by performing basically precise measurements at low energy, we have the chance to find information about high energy physics. So typically we start doing this at dimension 6, and at dimension 6 we have here a set of operators. So these tables are taken from the Varso basis of dimension 6 operators. You can see basically there are different types of operators. So on the right hand side we have the 4 fermion operators, and here on the left we have fermionic operators with 2 fermions, and also purely bosonic operators. So all these operators will basically change the interactions of the standard model particles, and by measuring these interactions we can basically extract information on these coefficients here. So on this ratio of basically C over lambda squared, which, as we've seen in the simple example of the Z prime, this combination here is related to the mass and couplings of the UV particles. Okay, so let's see how that works for the LHC. So what we have to do is basically take measurements of different observables. So we have the experimental measurement, and it's very important to, in fact, have very precise experimental measurements because we want to be able to measure small deviations from the standard model predictions. Then, having these measurements, we basically subtract what we know to be the best standard model prediction. And again, here we need to have precise standard model predictions, and these typically include higher order corrections. And of course, over the recent years, there has been a lot of progress for various processes being computed at next to leading order, and even NQ below for a few 2-to-1 processes. So these are the two things we need. And then once we've compared these two numbers, so the experimental measurement and the standard model prediction, so what we have to compare that with is the deviation that we would get from the effective field theory operators. So this difference basically will be proportional to the coefficient of the operators. We have to sum, of course, over all the operators which are entering in this observable. And then also we have the effective field theory predictions. So the first term that we have here is at dimension 6. But of course, one can systematically improve the predictions, including higher order effects in the 1/λ expansion. So the level at which this is done, and in particular also by the experimental collaborations, can be different. So one can take inclusive measurements or of total cross sections, or fiducial measurements of total cross sections, and use those to compare with the standard model prediction, and then get some constraints on the EFT. One can take differential parton level measurements, differential particle level measurements, or even do some analysis at the detector level. So all these are possible ways of doing it. And of course, by going down to detector level, it's a lot more complicated to do the analysis, but it has fewer assumptions, and potentially one can extract more information by doing it like that. The problem is, of course, the complexity. So typically in feeds that are done at the theory level, only the first two are used. So inclusive cross sections or differential distributions are the parton level. But of course, there has been a lot of discussion towards making progress, also including particle level observables and detector level analysis. And I also wanted to mention that a lot of this effort is also coordinated by the LHC EFT working group, which was formed last year. And I put here the link to the meetings of the working group. And if some of you are interested, you can always have a look and subscribe to the mailing list so that you get emails about the meeting. So there is a lot of work which is ongoing on different topics related to EFT. Okay, so well, the rest of my talk will focus a bit on exactly what we can do on the theory side about effective field theory predictions. So one thing which I already mentioned, one can improve effective field theory predictions by going to higher orders in the 1/λ expansion. And there are different ways of doing this. So one can consider the square terms coming from amplitudes with 1 dimension 6 operator when we square those amplitudes. One can have double insertions of dimension 6 operators, and also one can go to dimension 8. So in principle, all these terms are of the same order, and there is a lot of interesting work going on to try and investigate how all these terms compare, and eventually include as much as possible in our effective field theory predictions. Another direction, and actually this is the one I will be mostly discussing, is the fact that basically effective field theory is a quantum field theory, which means that it's renormalizable order by order in 1 over lambda. And that means that we can also compute corrections in the QCD and weak couplings of the standard model. So we have our linear predictions here, which go like 1 over lambda squared, and then one can improve these predictions by computing higher order QCD and electroweak corrections. So this is something which people have been working on over the last few years, and I will try also to show a few examples as to why these corrections are potentially useful and how they can help us to find more information about the Wilson coefficients of the EFT. So as a case study, I wanted to discuss a few examples from top-quark physics. So the advantage of top-quark physics is that it has a very rich phenomenology at the LHC. So we have the chance to produce the top quarks in different ways. So in pairs, in single top production, in association with a Higgs or a vector boson, but also we have access to processes where even though the top is not in the final state, the interactions of the top quark are very important because this set of processes involves top quark loops. So once we modify the interactions of the top quark, we will also change the predictions for these loop-induced processes like the ones I'm showing here. Higgs production in gluon fusion, Higgs plus jets, double Higgs production, Higgs plus Z in gluon fusion. So there is through these loop-induced processes, there is a clear connection to Higgs physics, and I will discuss this also a bit towards the end of my talk. So starting by basically trying to list the operators which change the interactions of the top quark. So these are the ones shown here. And then we also think about the production channels of the top. So you can see the possible channels here, and you can see there is some complicated picture where there are a lot of arrows of different operators entering different processes. And this is basically a simple way to realize almost immediately that we need to follow some global approach in what we do. So the fact that operators will be entering different processes at the same time, it means that if we want to learn as much as possible for the Wilson coefficients of these operators, we need to eventually consider all these processes at the same time. So let's see a couple of examples of processes and how these top production channels are affected by top quark operators. So the largest production channel for the top at the LHC is top pair production. So you can see here the leading order standard model Feynman diagram for QQ bar going to TT bar. So this is mediated here by gluon, which means that this TT bar pair is basically in a color-octet state. If we start thinking about the dimension 6 operators, which can modify this process, there is a set of 4 fermion operators which introduce these 4 fermion contact interactions like the one shown here in this diagram. So there are different types of these 4 fermion operators. And the differences between these operators are basically different chiralities and different color structures in these combinations here of quark fields. So one has the color octets, where basically the TT bar pair is in a color octet state, and also one has the similar set of singlet operators where the TT bar pair is in a color singlet state. So from comparing this here with the standard model diagram, it becomes obvious that some of these operators, which have different color structures, will not interfere with this leading QCD diagram of the standard model. So one way to lift this problem of no interference is to consider the weak contribution to the standard model production. So replacing this gluon with a Z. So that's one way of doing it. And then we get some small contribution at 1 over lambda squared. And the other way of doing it is basically also computing next to leading order corrections to this process, where we will get diagrams which will in fact interfere. So standard model diagrams interfering with the EFT diagram. So this is what we did in this work last year with my collaborator. So we computed basically this process, including next to leading order corrections, and we have results for all these operators, both at leading order but also next to leading order. And what is interesting to see is that by going to next to leading order, now the singlet operators give us a non-zero interference with the standard model. So this is good to have, in particular if one wants to perform a linear analysis for the EFT. These contributions are the ones which enter for the first time for the singlet operators. So another thing which we can look at by going to next to leading order is the impact of operators which involve 4 heavy fields. So the operators I was showing before had 2 light quark fields and the TT bar pair. But one can also look at operators which introduce this 4 top or BBTT interactions. So the typical place where we look for these interactions is by looking at 4 top production and TTBB production at the LHC. But it's not hard to realize that if we only look at TT bar production now at next to leading order, one gets contributions from these operators through these one loop diagrams like the one shown here. So you can see here now that we have these 4 top interactions entering at one loop. So one might wonder, why is it worth computing this? It turns out that some of these contributions are not that small, and potentially this computation can give us a new handle of information, which will be complementary to what we learn from TTBB and 4 top production. So eventually what we want to do is combine these contributions also with an analysis of 4 top and TTBB production and see what we can learn about these 4 heavy operators. Another thing which we can do is try to find observables which are sensitive to particular operators and also sensitive in a way that they break degeneracies between different operators. So there are cases where 2 operators can have the same impact on a particular process, and this can be this problem can be solved by finding observables which exactly break that kind of degeneracy. So one example that we looked at last year was an asymmetry observable in TT bar plus jet production. And you can see here in this 2D plot how this energy asymmetry observable, which is shown in red, can help to break the degeneracy between these two four fermion operators, which have different top quark chiralities. So you can see that this observable seems to work better than the typical charge asymmetry and also better than the inclusive cross-section for TT bar plus jet. So this is something that we always have to keep in mind, that when we try to learn about this Wilson coefficients, in a lot of cases, it's very useful to think and to optimize our observables to have the best possible sensitivity and also to break degeneracies between operators. Again, in the same spirit, one can try to find optimal observables for single top production. And I'm showing here an example where the top polarization angles can be used. And in this particular case, they can be used to look for signs of CP violation by basically having here a Wilson coefficient for this dipole operator, which has an imaginary part. So by finding the right observable, one can see that one gets an asymmetry here in this angular distribution. And the only coefficient which gives such an asymmetry is exactly the imaginary part of this Wilson coefficient here of this dipole operator. And this is the CP violating part. So again, this is just a matter of finding the best and optimal observable to exactly probe the interactions that we are interested in. My final example from top physics that I wanted to mention is the production of a single top in association with a Z boson or a Higgs boson. So so why should we be interested in this class of processes? This is an interesting set of processes because there is a very interesting interplay between single top Higgs, single top Z, and single top production. So you can see here that there are a lot of different operators which modify these channels, and there is even a connection to Higgs operators and the operators which change diboson production. So what we did a couple of years ago was to focus on this process and try to look if to establish whether some of these operators can have a large effect on the cross section and distributions for this process. So one way of doing this is by thinking about the underlying process of BW scattering to top Z. So what we did was to look at the helicity amplitudes for this sub-process. And what we find is that for some of these operators, we get amplitudes which grow with the energy. So in the standard model, there are some cancellations between different diagrams, which get spoiled if we start changing some of these interactions of the top with the Z. So these amplitudes which grow with the energy means that we are going to have large deviations in the differential distributions. And we try to quantify this by looking at the sensitivity of this process with current measurements, but also in the future when we will have differential information for this process. So I mentioned this process because it's in fact a rather rare production channel of the top. So this has been measured for the first time at the LHC. It has a small cross section compared to TT bar and single top production. But what we find, just because of this energy growing contributions, that especially when we have differential information for this process, this can give us a lot of information for some operators, and it basically motivates using using this process and also differential information for this process in a global fit. So I've shown different examples where we try to compute the effect of different operators on different observables, and also on top of the leading order predictions to include higher order effects, so one loop contributions and QCD corrections basically. So to help with this effort, we also last year released a model. So this is basically a piece of software which can be used in Monte Carlo generators in order to compute this next to leading order QCD corrections in the SMEFT. So I'm pointing here to the website for this work, and this is very useful because it can be used basically to compute a lot of different processes. It includes the Varso basis operators under a particular flavor assumption. And basically what we can use it for is to compute a lot of different Higgs, top, and gauge boson production channels for the LHC, and also compute for these processes the QCD correction. So we think that this is going to be very useful for the SMEFT program at the LHC. Okay, so I've shown some examples where we compute the impact of effective field theory on different processes, and how we also compute in some cases higher order effects, and how these have been also included in Monte Carlo generators. So let's see how we can use these predictions to perform global fit. So eventually the goal is to constrain the coefficients of the dimension 6 operators, and from these constraints basically learn about UV physics. So I've already mentioned that top-quark physics has a very rich phenomenology at the LHC. There are a lot of different production channels, and by basically including a lot of different measurements, one can hope to constrain the interactions of the top-quark. And it's clear that when we're trying to do it, it's very important to include different channels. And this is what I'm trying to show here in this 2D feeds. So what is shown here is the constraints that one gets from different observables involving top quarks, in terms of breaking degeneracies between different operators. So the first two operators here have different quantum numbers, and you can see here that by including TT bar production, but also TT bar in association with a vector boson, one gets a constraint here, which is a lot more stringent to what one would get by only including, for example, top pair production measurements. And the same thing is shown here. Here we have two operators which are different in the chirality of the top. And then you can see that by combining TT bar and the charge asymmetry measurements, one can really constrain the Wilson coefficients of these operators. So it's clear from these examples that by including as many processes as possible, we can really give stringent constraints to these Wilson coefficients of top operators. So of course, when it's not that simple to do a fit. So we need to remember that our starting assumption was that basically we don't have enough energy to produce these heavy particles that we have integrated out. So we need to make sure that whenever we do these fits, we are in the region where the EFT is valid. So we need to make sure that for a given value of lambda, we are not probing energies which are close or larger than lambda. So we need to basically make sure that our results are not dominated by the high energy beams. Another thing which we need to keep into account is that there are some theoretical constraints which can come in for the Wilson coefficients. These are basically constraints from perturbativity, unitarity, and there are also UV completions which can tell us what kind of range to expect for various Wilson coefficients. So this is something that one can use as an input to the fit, or one can basically leave the coefficients completely free and then see what data tells us. Another thing which is discussed quite a lot is this contributions which come from squaring the amplitudes of the dimension 6 operators. So these are contributions which come in at 1 over lambda to the 4th and are of the same order as the interference of dimension 8 operators with the standard model. So typically these contributions are large compared to the linear terms if there is some suppression factor like helicity or color. So if the amplitude for the EFT does not interfere with the standard model amplitude due to helicity or color, then these 1 over lambda to the 4th contributions are basically the leading contributions that we get from those particular operators. And another thing which can happen in a fit is that if the constraints that we get from the experimental measurements are not very stringent, it means that our operator coefficients are loosely constrained, and because these quadratic terms go like c squared, they can end up being larger than the linear terms. So I will show some examples where we do this comparison of including or not including this quadratic terms. And yeah, you can see the first example here. So this is what happens when for these 4 fermion operators, we now go from the linear case to the quadratic case. And you can see here that this is actually a very zoomed in version of this plot with the range going from -5 to 5 compared to what we had before. So basically in this case, by including these quadratic contributions, the bounds that we get on these operators become a lot more stringent. So with the precision that we have right now for these measurements, these quadratic contributions are still important. Okay, so we've seen that it's very important to compute, to include in our fit different processes. So we would do that. So we will put everything into a global fit. So one thing we always need to do is to make sure that our standard model predictions are the most precise that we can have. And then we include a lot of different data. We need to take into account all the uncertainties. We need to make sure that any information that we have on correlations between uncertainties from the experimental measurements, all that information has to be included in the fit. And then when we put all these things together, we get constraints on the Wilson coefficients of the operators. And we can use those constraints to also bound UV complete models. And we need to basically have a setup where new data can be added in a straightforward way. So this is just a list of all the data which we include for a top fit. You can see it's a lot of different channels, top pair production, the asymmetry measurements, 4 tops, TTBB, TT Barn association with the vector boson, then single top production, single top with a W or a Z. So these are both total cross-section measurements, but also a lot of differential distributions. So we end up with about 150 data points for top production. And we try to use these data points to constrain the interactions of the top. So you can see here a comparison between the bounds that we got when we did this fit 2 years ago compared to the most recent fit from this year. So what one can see is that as we expect, by basically adding more data and more luminosity into our measurements, all these bounds improve in the latest fit. So one can see that, of course, different operators get more or less stringent constraints. So the one which is most constrained is this dipole, chromomagnetic dipole moment of the top. This is this constraint is mostly coming from TT bar production. And then you also see the constraints that we get on the 4 fermion operators. So the operators which are not very well constrained are the ones which involve 4 heavy fields. So these are the ones that are constrained from 4 tops and TTVB. And because those measurements are not yet very precise, the constraints that we get on these operators are not very good. So another set of operators which is not very well constrained, and you can also see this in this other fit, which came out a couple of years ago. So what you can see maybe a bit more easily in this plot is that some of these operators, we basically had the coefficients divide by 10 to fit in this plot. So this means that these operators are basically very, very loosely constrained. And these are, in fact, the operators which change the interaction of the top quark with the Z boson. So I'm bringing that up here because you see that this is also important when we want to combine Higgs and top. Okay, so I've shown the results that we get for a global fit in the top sector, but let's now see how we proceed to combine with the Higgs. So we know that the EFT has basically a very global nature, which means that there is interplay between different sectors, and the interplay is particularly interesting between the top and the Higgs sectors. So one obvious place where one can see this interplay is by looking at TT bar Higgs and the loop-induced processes producing the Higgs, either on its own or in association with jets or in double Higgs production. So what people realized already some time ago is that basically by combining this set of processes, one can break degeneracies between the different operators and learn more about the Wilson coefficients of the different interactions. So what one can see here is basically that one can combine the differential measurement of the Higgs PT with the TT bar Higgs production to break the degeneracy between the top Yukawa. So this is basically changing the interaction of the top with the Higgs, and this contact interaction, which is shown here in this green blob between the gluons and the Higgs. So you can see in this plot that basically combining different processes, we really break these degeneracies between the two interactions. And we can do this because these interactions have a different effect on the different processes. So the top Yukawa is just a rescaling of the TT bar Higgs and Higgs cross sections, but this contact interaction of the gluon with the Higgs will give a much harder distribution in the tail for the Higgs PT. So taking this into account, one can also use this boosted Higgs measurement, which is shown here in gray, to help break this degeneracy. So there is definitely an interesting interplay thinking about this Yukawa interaction and this contact interaction between the gluons and the Higgs. But the interplay becomes a lot more interesting if we also think about the operators which change the electroweak couplings of the top. And you can see how interesting, or rather complicated, this interplay becomes if we consider all these processes which are loop-induced. So we have all these gluon-gluon processes going into a Higgs, Higgs plus Z, double Higgs, Higgs plus Z, or even the offshore Higgs production and decay into two vector bosons. So basically what this tells us is that in the end, there is a very deep connection between the two sectors. And this is something that motivates us to combine the two in a global fit. So how does this interplay work? So these operators here, which change the coupling of the top with the gauge bosons, are typically searched for in single top, in TT-bar production association with the vector boson, or single top production association with the vector boson. So these are basically these blobs here, the ones we are trying to constrain. But the same operators introduce also new Higgs interactions, and these are the ones which enter in Higgs processes. So this gives us a motivation, because exactly as I was saying when I was showing the results of the global fit in the top sector, these operators are not yet very well constrained from top measurements. This tells us that basically if we combine the two, we might hope to learn more about these operators. So with this motivation, we move on to combine basically Higgs and top into an even more global fit. So by adding a lot of Higgs measurements to our top fit, so these include different production channels of the Higgs. These are both inclusive cross-sections and also differential distributions. Of course, when we do that, we realize that we also have a lot of new degrees of freedom. So these are operators which did not really modify the top production channels, but now enter in the Higgs production channel. So that means we have now new degrees of freedom, and we need to take those into account in our fit. So you can see here schematically how different operators change different channels, different production channels of the Higgs. So this is shown by all these colored blobs in the Feynman diagrams, and you can see one can have different effects. So there are operators which change the inputs. There are operators which modify existing vertices. There are operators which introduce new vertices which are not there in the standard model. So there is this rather complicated picture of a lot of different operators having different effects on different processes. And we try to see basically what we can learn from different processes on these Wilson coefficients of the various operators. So we try to quantify this a bit by looking at this Fisher information table. So what this is supposed to show is how much information we get on a particular coefficient from different processes. So we have a lot of 4 fermion operators which are constrained by top-quark measurements. But what is maybe more interesting to see is what happens with the top Yukawa and the chromagnetic dipole moment of the top, as well as the operators which change the top to Z coupling. So what we see from this Fisher table is that, in fact, these loop processes with the Higgs, so the Higgs in the final state, have an important impact on constraining some of these top operators. So there is a very interesting interplay between 3-level processes, such as TT bar plus Z, and this one loop, for example, decay of the Higgs here into a photon and the Z. So this interplay is again obvious, and one can also try to quantify how we use the different processes to break degeneracies between different operators. So these are in fact the operators which I showed at the beginning. So this is the top-Yukawa, and this is here the interaction of the gluon with the Higgs, the direct interaction between the gluons and the Higgs. So one can see that basically by combining a lot of different processes such as TT bar, Higgs production, differential Higgs measurements, one can break the degeneracies between these interactions. And this is also shown in this work in another global feed, which was done by John Ellis and his collaborators at the end of last year. So again, this stresses how important it is to be as global as possible when we do this when we do these feeds in the SMEFT. I also wanted to show how this interplay comes in again, looking at the interactions of the top with the Z. And one can also see the impact of adding these loop processes, such as the gluon to Higgs plus Z. And you can see how this enters. So this is this purple contribution shown here, which is not there at leading order. And you can see how this is able to exclude quite a bit of the of this negative region here for this coefficient here, which changes the coupling of the top to the Z. So by basically including as much as possible, and also the both from the data side, but also from the prediction side. So the fact that we can include now this contribution here, because we can compute these one loop diagrams, is very important, because you can see that it can help us to constrain some of these coefficients. Okay, so we can, I'm getting to my last couple of slides. One can also systematically check how adding the Higgs data affects this operator. So this is a comparison of a top-only feed with a feed where we include also Higgs measurements and also the dye boson measurements from the LHC. So you see that all the operators which are only shown in orange are new in the global feed. But what I wanted to stress here is that for some of these operators, you see that there is an improvement, even though by adding the Higgs measurements, we also add a lot of new degrees of freedom. We still have some improvement on the bounds that we get on some of these top operators, which is related to the stuff I was showing before here with the impact of these one loop contributions. Another thing which we can do is to check what happens systematically if we include next to leading order corrections in these feeds. So this is what is shown here. So as I said, by going to next to leading order, we resolve this problem of non-interference for the color singlet for fermion operators. And these are in fact the operators which are mostly affected by going to next to leading order. You see there is a large difference between the blue and the orange. Basically, when we are at the linear level at leading order, these operators are unconstrained. But when we include these next to leading order corrections, we start getting constraints on these coefficients. There is also an effect for the quadratic feeds. Again, some of these operators are affected by next to leading order corrections, even if we include now the quadratic terms. Another thing which I mentioned at the beginning is the impact of these square terms coming from squaring amplitudes with one EFT insertion. And this is what we're trying to compare here. So we compare a linear feed, which is shown in orange, with a quadratic fit, where we include these contributions from the squared dim6 amplitudes. And you can see that for quite a lot of operators, there is in fact a large difference between the bounds that we get. And this is particularly true for fermion operators. And this basically tells us that with the current precision that we have on top measurements, these quadratic effects are still very important. This will improve when we get more precise measurements. So for some of these operators, things will get better in the sense that eventually orange and blue will get closer to each other. But of course, there are still operators where even with a lot more luminosity, this will not completely go away. And these are particularly the operators which don't interfere at leading order, because even when we go to next to leading order, these linear contributions are typically small. And this is one other thing which we have the flexibility of doing is trying to check what I mentioned already. What happens if we remove high energy beams from our feed? So we want to make sure that we are not completely dominated by the high energy region, where we should start worrying about the validity of the EFT. So we do this here by basically not including in the feed data points which are above 1 TeV. And you can see that most operators are not really affected by this. So there are a few operators which seem to be affected. These are 4 fermion operators which enter in TT bar. So one can see that there is some effect in the bounds when we in fact include or exclude these high energy beams. So this is something that one has to systematically check and make sure that these effects are not huge. So we want to make sure that whatever bounds we get are not really coming from regions where the EFT is not valid. And the final thing that one can do with these global feeds is to apply theory restrictions. So one can, for example, have some particular UV complete model which constrains some of this or relates some of the coefficients of these operators, such as like a top-Higgs scenario, which basically gives us a smaller number of degrees of freedom for the top operators. And one can see what happens with the bounds. So here, by correlating some of these degrees of freedom, some of these bounds get more stringent. So this is something that we've set up in the feed to be able to do all these things, because these will be very useful also in the future. So the next and natural question is like, what do we do with all these bounds? What do we learn from them? So one can basically translate these bounds to constraints on parameters of UV models. And the simplest case, which I take from this paper by John Ellis and collaborators, the simplest thing that one can check is what these bounds of the Wilson coefficients, what they mean for single field extensions of the standard model. So you can see here that for different extensions, one can set limits on the mass of any possible new resonances. So this is something very interesting. So in the end, this is the goal of the whole program, that we want to learn about UV physics. So this is something that requires a bit of work, and this is something that people are working on. So making sure that what we get is actually used to learn about UV complete models. Okay, so that brings me to my conclusions. So the SMEFT is a consistent way to look for new interactions and search for heavy new particles by making precise measurements at low energies. So having control on the predictions in the SMEFT and also higher order corrections, these one loop contributions in SMEFT predictions can improve our sensitivity. And this is why we've been working very hard to get this computed. So the global feeds are there. So at least on the theory side, there has been a lot of work to put a lot of different data together and constrain a lot of operators. So it's important to include the best predictions that we have, and also to combine a lot of different processes. And eventually we want to take our global field results and see what we learn about UV physics, and this will give us basically a clear indication of the scale of any potential new particles. And that's it from me.